Welcome, ladies and gentlemen, to another exciting episode of Dave Does Math from Home. We got a good one for you today. Today we are talking about tangent planes. We've explored directional derivatives, partial derivatives, gradients. We have a really solid foundation of what derivatives are and how they work. So now it's time we started putting them to use, and we looked at some of the things we can do with three-dimensional derivatives on three-dimensional functions. And one of the most important things we can do is tangent planes. This is the idea of linear approximation. This was a big deal in Calc 1. In Calc 1 we were constantly using derivatives to find the tangent lines, the equations of lines that were tangent to a function at a certain point, because those tangent lines are linear approximations of this curve. And if you can approximate a curve, even a really complex, weird curve, with something linear that sort of matches what it's doing, locally at least, then that gives you a lot of sort of computational power over this thing, a lot of predictive power. They're very useful in a lot of, maybe not industries, but maybe industries, I don't know. It gets used a lot in the real world, this idea of linear approximation. I think it gets used in business a lot, so I don't know if that counts as an industry. Maybe. Anyway, I wanted to talk a lot about how to find tangent planes and these linear approximations in 3 space. But before I get deep into that, I want to first talk about how to get tangent lines in 2 space, because that'll be a really good review. And if you can connect the things that we're doing here to the things that we did a year ago in Calc 1, I think that making sense of this will be much, much easier. So the first thing we're going to do is we're going to find just a pretty standard issue 2-dimensional function. So let's do y equals negative 2x squared plus 6x minus 3. Here you go. This is a parabola. It opens downward, some kind of polynomial. It's very, very straightforward, very typical. I want the tangent line at x equals 2. So, to get a tangent line, we need 2 things. We need the slope and a point. We have half of a point. We can get a y value by plugging this into this equation. That will give me 2 squared is 4, times 2 is negative 8, plus 12 is 4, minus 3 is 1. Okay, so I have a real nice point here. The point is 2, 1. So I do need that y value. That'll be important later. And now I need a slope. The slope I can get by finding the derivative. Y prime, I'm not going to use y prime. I'm going to use dy dx. The derivative is negative 4x plus 6. No surprises there. At x equals 2, the derivative is negative 8 plus 6 is negative 2. So this is my slope. You can get your slope by finding the derivative and evaluating the derivative at your point. Very straightforward there, still no surprises. I have a slope now, I have a point. I can use our handy dandy y minus y1 equals m times x minus x1. This is point slope form. This will give me the equation of a line. Y minus 1 equals negative 2 times x minus 2. So y equals negative 2x plus 5, I think. Great. That's it. So this is us finding a point, finding a slope, plugging them into the equation, getting the line. With that in mind, let's see what happens when we do this in 3 space. So let me get a marker that's a little more robust. And let's do something like z equals negative 4x squared minus y squared plus 13. This is kind of similar to what we just did in 2-space. This is a paraboloid. It's not quite a parabola because it's three-dimensional. It's much narrower on the x-axis than it is on the y-axis. So it's not like a round paraboloid. It's like a squished oval paraboloid. But that's fine. It opens downward, and the intercept is at 13. So we have some sense of where this is. I want the tangent plane at x, y equals 1, 3. So, just like in the last problem, the first thing I'm going to do is I'm going to plug 1, 3 into the equation so that I have a z value that I can work with here. If I plug in 1, 3, then I'll get z equals negative 4 minus 9 plus 13. That's unexpected. I know I copied this equation down from a piece of paper, but literally all I wrote down was the equation. I didn't actually do the math yet. It's just an equation. I was not expecting to get z equals 0. That's neat. Okay, so I'm getting z. Actually, let's actually change this. Let's say that this is like 15, so that I can get an actual z value, so that we can see what happens with this 2. Zeros are easy to work with, but they don't make for great examples. Like, it's hard to see where this piece of information gets used and where it comes in and how it affects this thing if it's a 0. So, slight change of plans. This is a 15, that's a 2 now. Let's move on to phase 2 of this. I need slope. In the last problem, there's only one slope. X increases, that's the only really dimension you're playing with here, so that's it. Here, there's lots of different directions we can go. We have an entire plane worth of independent variables we can wander around in. So we need a couple slopes. We need a slope on the x-axis. I'm going to call that dz dx. That's going to be negative 8x. That's the partial derivative with respect to x. And at 1, 3, this is going to equal negative 8. So that's my slope in the x direction at this point. In that direction, sometimes this gets written as mx. That's the slope in the x direction. We also need the slope in the y direction, which is going to be negative 2y. So at 1, 3, that'll give me negative 6. That's my slope in the y direction, that's my. So I have my slopes, I have my point, I can start plugging stuff in. There has to be something for me to plug stuff into. So let's talk about that. In 2 dimensions, we have this point slope form. Y minus y1 equals m times x minus x1. This is the 2-dimensional version. Y minus y1 equals m times x minus x1. So hopefully it's not too much of a stretch for you to believe me if I say that the 3-dimensional version of this is z minus z1 equals mx x minus x1 plus my y minus y1. We're basically just attaching another term to this. You have your slope in the x direction paired with the x coordinates. You have your slope in the y direction paired with the y coordinates. It's not bad. It kind of matches. We're really doing the exact same thing. We're just adding a couple more letters to it to make it more fun and exciting. So for this problem, I will get z minus 2 equals negative 8 times x minus 1 plus negative 6 times y minus 3. Just like in this one, whenever we talk about this one, I always try to emphasize y and x are variables. They stay variables. You don't mess around with those. x1 and y1 are your point, just like x1, y1, z1 are a point up here. And mx and my are your slopes. So we're plugging in numbers for z1, mx, x1, my, y1, and we're leaving x, y, and z alone so that this thing still comes out to be some sort of three-dimensional function. And now we can simplify it. Z minus 2 equals negative 8x plus 8 minus 6y plus 18. So I think the final simplified version of this should be z equals negative 8x minus 6y plus 28. So this is our linear plane, and you can see that it is in fact a plane. It's got a slope on x and a slope on y, and that thing equals z, and we have an intercept over here. It's 28, and it's nice. It works out. And it kind of makes sense too. If this is a paraboloid with an intercept up at 15 that's going down in all directions, we would expect something out here to have negative slopes. Like it's like you're going down from the top of the thing as you go outwards on x and y. It's pretty steeply downhill in both of those directions, and if you go backwards, the intercept is up to 28. So that's a good first example. I'm gonna go straight into a second example so we can see what this looks like with a slightly weirder looking function. And then we're going to talk about implicit three-dimensional functions. But don't panic, we're not doing implicit differentiation. Honestly, the implicit version of this is going to be just a very, very slight variation on what we just did. But that's for later. It's probably going to be in a part 2 of this video. First, I want to do z equals e to the xy minus xy. I want the tangent plane at 0, 2. So, first thing I need to do, I need a z value. If you plug in 0, 2 into this, you should get e to the 0 minus 0, which should just be 1. So, I have my z value. Now I need some derivatives. dz dx should be derivative of e to the something is e to the something times the derivative of the inside. So this is e to the xy times y minus y. Which, if you evaluate at 0, 2, will give us still e to the 0 times 2 minus 2. So I think that should give us 2 minus 2 is 0. Okay. I also didn't get very far in the planning of this one, so if this turns into a really boring plane, we can change some things. And then dz dy is e to the xy times x minus x, which going to be also 0 because both of these things are 0. Okay, so this is a very poor choice of tangent plane, and I should abandon this and do something else. The tangent plane is z equals 1 because there's no slope on the x or the y at this point, apparently. I chose poorly. I could probably fix this just by adding like a 2 here. Now this is minus 4. There's a negative 2 here. And this is still 0. Yeah, okay, here we go. I fixed it, kind of. It's going to change my z-value as well, though. The z-value is now still e to the 0 minus 0. No, it doesn't change my z-value. Z-value is still 1. But now I have an interesting slope along the x-axis, so that will help. So, I have my two slopes. This is mx. This is my. I have my point. I can plug everything into the function. Z minus z1 equals mx. X minus x1 plus my. Y minus y1. So, plugging stuff in, we get z minus 1 equals negative 2 x minus 0 plus 0 times y minus 2. So, z equals negative, no, I'm trying to go too fast. Z minus 1 equals negative 2x. Z equals negative 2x plus 1. That's my tangent plane. Doesn't involve y because there's no slope along the y-axis. So as you move up and down the y-axis, it's not increasing or decreasing, it's just flat. And that is represented in there being no y values here, or no y representation here. Y doesn't matter to this tangent plane. Sorry that got a bit muddled in the middle. We had to change equations halfway through. I guess we've had to change both of these equations halfway through. That's a little embarrassing, but not embarrassing enough for me to re-record this. So I hope that my embarrassment is entertaining. We got another one of these coming right up where we're going to talk about how to do this with implicit functions, so stay tuned.